This is FE Peer Review. The date is July the 27th, 2021. Measuring a black swan, a critical look at platform habitat. I've been working on this video for over 2 weeks, and I'm not done with it yet, and I went back and watched the 35 minutes of stuff I'd put together up till now, which is way too long, and it was more boring than Eric Dubay. So I'm just going to try to move through this material a little more quickly and maybe leave a few things out, but I hope it's still useful. Bob, the science guy who has the Research Flat Moon channel, did a series of videos looking at the black swan, so-called black swan platform habitat. He did an excellent job of it. Covered everything, covered all the bases really well. I don't really have anything to add per se, except that I thought I'd like to get into just a few points and go a little deeper into a couple of small points that he brought up. So I recommend you check Research Flat Moon and watch those videos. The main thing I'm going to be doing in this video is analyzing close-up image of platform habitat and comparing it to the highly refracted image that BMLSB produced a few years ago. And kind of being a little analytical about what actually do we see happening in atmospheric refraction. What's compressing, what's extending, what parts of the structure are changing. I think it's kind of interesting, and it's a good example, this photo. But along the way, I had an exchange with BMLSB, a comment exchange, and I just wanted to touch on that. BMLSB says that Bob, in comparing two different platforms, Habitat and Hill House, what he is showing to Brandon on what he thinks is missing from the lower portion of Habitat doesn't exist because he's comparing Hill House to Habitat. BMLSB is mistaken here. He's comparing the substructure below the boat landing deck, and he's saying that, if I understand him correctly, he's saying that Habitat simply doesn't have such a substructure visible above the water line, which is why we don't see it. So it's an apples to oranges comparison. Well, that's not true. It's got an almost identical arrangement of elements to Hill House, and I'll show that in a minute. So I responded, platform habitat and Hill House have very similar supporting structures. This is a fact that's easy to verify, etc. I then also gave him a link to marine biophotography. I'll show the images from that. He responded, they are similar to most but very different. I responded, all similar but very different. Sorry, I don't follow that. Bob showed part of the permit documents for platform habitat and used those dimensions. At that stage of the analysis, Hill House had nothing to do with it. He could have ended the analysis there, and it would not have changed his point. The point being that roughly 15 feet of structure shown in the permit documents and visible in the photos on the website I linked to above is not visible in the black swan photo. Okay, let's take a look at a few things here. I'm going to show you first a few images of the two platforms just to get you oriented in case it's not familiar to you. This is from marineBiophotography.com. This is platform habitat, and what we see is there's the water line here and what I'm calling the substructure, which is the structure between the water and what's called the boat deck. That's where people getting off boats arrive. From the boat deck, you go up to a level 1, and then a level 2, and then finally there's a helipad up at the top. Those are the main elements that I'm referring to throughout. And this is platform habitat. Here's another view of platform habitat. And another. These are nice close-up views that show no distortion due to distance effects. And then finally here is platform Hill House, which we also see has a substructure, a boat deck, a first level, a second level, and a helipad. Now the proportions of Hill House are a little different than platform habitat. The heights floor to floor, level to level are a little different. But in terms of how they're organized and all, they're very similar. This is another image from Jennifer Schwartz that I got from Getty Images, and this is an image that I'm going to use to do the comparison of the undistorted structure versus the distorted image that's because of heavy atmospheric refraction. This here is an image from BMLSB69's video showing the heavily distorted version of habitat on the left. And this is another from the same video, which I'm going to be using for the analysis. Before we dive into the analysis, I want to touch on one more point here, which is the importance of recognizing when your data is not entirely correct, garbage in, garbage out, as the saying goes. There was a comment from Random String, who is not a flat earther, and it was all in all a respectful and helpful comment. It was on Bob's channel, but I think Random String got something wrong here, and it's a worthwhile exercise to see what went wrong. Random String says, "It seems to me that looming and compression can happen at the same time. That was the thing I addressed to my mail to you. It seems to me that in the photo of habitat you're discussing, nothing of the platform is actually hidden." Bob had said that the substructure below the boat landing deck, which we see in the bottom image, is hidden by water, which we see in the top image. Random String is saying, no, it's not hidden. The big lump, the boat collision barrier, at the bottom left part of the legs of the platform that we see on the Black Swan image, and Random String has circled that in yellow in the upper left here, is also visible in the clear photo of it, and it sits just above the water. And here I don't know if Random String is a man or a woman. Anyway, Random String has circled it again here in the bottom. So Random String is saying that this sort of lumpy thing we see here is also being seen here. And this is what I think Random String got wrong, because we are comparing, again, apples to oranges. It's the same platform, but these two photographs were taken on different days at different times. We don't know when these two photos were taken. And I will show you something interesting in a couple of the platform habitat photos. In this photo of platform habitat, we see the boat deck, and we see below the level of the deck a black object on the right side and another similar one on the left side. Now we look at this photo of platform habitat. It's taken from the opposite direction, but it's the same platform. And we see that in addition to those black things that were below the boat deck, there are now boat collision barriers of stacked tires above the level of the boat deck. So apparently these stacked tires are things that are not always there. In this photo they're there. In this photo they're gone. I believe that Random String is comparing two different photos, and in the upper left photo we are actually seeing those tires, whereas in the lower photo those tires are not there. So I think this was a good lesson in the importance of being careful about what your data is actually showing you. It's easy to see in it what we want to see. Of course, there's always that problem, but simply to misinterpret what we're seeing in it as well. In best possible conscience, it's easy to make a mistake like that. In order to do the analysis, I had to get some hard data in terms of the dimensions of this platform. And to do that, I went to the Bureau of Ocean Energy Management, which is part of the Department of the Interior. They have a page that has permit documents for all these different platforms off the coast there. And what you're seeing is a screenshot from that page, as well as the highlighted in gray. That's the permit document that I am working with. It gave me the dimensions for this platform. There's going to be a small issue regarding one dimension that was discussed in Bob's video, and I'm going to hopefully offer a minor correction on that point. Anybody wanting to do a real thorough analysis of this image, I think needs to take the following into account. This is the cover page of the permit document I'm referring to. And this shows a diagram of the entire structure all the way down to the ground, to the dirt mud line below the water. the water line is quite far up on the page where it says MLLW. We will take a look at that more closely. So here's a clip of that same image, and I've got MLLW, which is mean lower low water. And that's the definition for the average low tide. So they take the average low tide, and they take the low tides and average them out over a 19-year period. And that low that they get from that is the MLLW. That's the baseline, basically. And in this case, this particular platform, the boat landing level was placed 15 feet above that line. Now keep in mind that that's an average, so there will be occasions when low tide is lower than that, and there will be occasions when low tide is higher. But it's also the low tide mark, so that means most of the time the tide's not at its low. Most of the time the water level is going to be above that line. When it's at high tide, it could be well above that line. So this 15-foot dimension here is effectively the largest on average. The largest on average. At times it will be a little more. But most of the time it will be less than 15 feet, considerably less than 15 feet. This is a tide chart of 1 month's data from June to July, and it shows MLLW on the left where I'm circling the mouse, 0.0. That's the mean lower low water line. And we can see that it drops a little bit below that on these low tides, and then it's a little bit above that, and then it drops down below again. And at its lowest point, the low tide was 1.6 feet below the MLLW. The average, the mean, is somewhere at around 2.5 feet above. That means it's fluctuating at roughly 2.5 feet above MLLW. And the high tides were as high as 6.7 feet above MLLW in this 1 month period. Now, 1 month is not representative of the whole year. There will be other months that have larger extremes as well as months that have lower extremes. I'm bringing this up because I think what we're going to find is if we study the photographs carefully, the distance from the water to the boat deck that we are seeing in these photos is not 15 feet. It's considerably less than 15 feet, and that'll become apparent shortly. So how I did this analysis, I did this analysis using my favorite graphic tool, which is SketchUp. I do my professional work in SketchUp. It's not really designed for this kind of thing, but it works pretty well for this purpose. So what I did was I imported an image of platform habitat that we see here from Jennifer Schwartz. I chose this image because it's taken close enough that we're not getting atmospheric distortions, but it's far enough away that we're also not getting a lot of very up-close perspective convergences. And it's also a pretty much straight-on shot of the side view of the platform. It's not exactly straight on, but it's very close to being a nice elevation view of the side. The platform dimensions I took off that permit document. So what I did was I imported the image into SketchUp, and then I had to scale the image because SketchUp doesn't know how big to make the picture. I needed to scale it up to an appropriate size. I wanted it to be basically full size. So what I did was I got dimensions from the permit documents. It was 25 feet from the boat deck to the first level, and it was 17 feet from the first level to the second level. So I drew these guidelines. You can see the dashed lines off to the left here. I drew those, and those are 25 feet and 17 feet. I drew those on here, and then I imported the image, and I scaled the image up until the second level, the first level, and the boat deck aligned with those three guidelines. That gave me a scale factor for the whole image. I scaled the whole image vertically and horizontally with the same scale factor, and that was the baseline. And then after I did that, I continued to add guidelines for dimensions that were not given in the permit documents. So I could see from scaling off the photo that from the second level to the helipad was 35 feet. From the helipad to the top of this tower here was another 42 feet. And then I also drew the line 15 feet down from the boat deck, which was the 15-foot dimension off the permit documents. And as we can see, the substructure is actually going into the water closer than that. It's not 15 feet down. And that's because the water is not at its mean lower low water line here. The tide is higher up than that. So that's how I got the image into SketchUp to make this framework, this baseline. And then what I did was I brought in the refracted image, as well. And in order to be able to compare them side by side, I had to pick a common dimension. So what I chose to do was take from the boat deck to the very top of the crane, and that would be this top horizontal line and this bottom horizontal line, and keep that as a baseline between the two images. I'll zoom out a little bit so you can see them both side by side. So we have the tops of the cranes aligning, and we have the boat decks aligning. And then what I did was I drew horizontal lines at the helipad, at the second level, and at the first level on the refracted photo, and I compared that to where they are on the baseline photo. And as we can see, the dimensions change. So taking it from the top, the upper portion of the crane, from the helipad to the top of the crane, is compressing. Whereas it was 42 feet on the baseline photo, it compresses down to 32 feet on the refracted image. The area from the second level to the helipad is expanding significantly. It's extending from 35 feet to 52, apparently 52 feet. That's how it looks. You can see the way these lines get farther apart. The second deck to first deck also expands from 17 feet to 19 feet. So these lines have also gotten a little farther apart. And then the lower portion has compressed considerably from 25 feet down to 15 feet. I've given the same data here, but in the form of ratios and percentages. And then finally, the substructure has just completely disappeared. Now, some people, including BMLSB, might say that it's basically infinite compression, that the zone below the boat deck is there, but it's compressed down to nothing. I don't know of any natural phenomenon that would cause that. It's simply not there in the image on the right. It's infinite compression or it's hidden by water. Fight it out. You guys can argue about it. I just simply wanted to show here that what we get with atmospheric refraction can include both compression, which we're seeing at the top and the bottom, and extension, which we're seeing in the middle. Now, take another highly refracted image from another day when the atmospheric layers are disturbed in a different way, and you might come up with a very different arrangement of distortions. It would make an interesting exercise, and BMLSB has lots of images to work with. He could do that if he wanted to get analytical about this process. So we're seeing horizontal bands, we're seeing both compression and extension. In maintaining a constant vertical dimension between the boat deck and the top of the tower, what I found was that the refracted image apparently got narrower, whereas the original was 135 feet from the leftmost pylon column to the rightmost column, three 45-foot spaces. The refracted image got narrower relative to its height. So in keeping the height the same, the structure got narrower. Now, I'm not saying that the height actually was the same. We don't have angular measurements of angular size for these images, and we don't really need it. It's just a question of proportion is what we're looking at. So in seeing that it apparently got narrower compared to its height, I thought we should do a comparison looking at the proportions of that effect. So keeping the 135-foot width constant between the two images, and now you see I put the refracted image above, and I've made it the same width rather than the same height. The result is that it appears to have gotten taller, 136 feet versus 119 feet. And then I drew these rectangles, which I shaded, in order to block out the key dimensions here and be able to do a side-by-side comparison. So what we see is that the smaller rectangle of the same width is the unrefracted image, or I should say the clear day standard refraction image. The taller rectangle shows the heavily refracted image. So the heavily refracted image extended upward. For the given width, it got taller. So not only did we see within it both compression and extension, but in sum total, it extended upward. All right, we're at the 20-minute mark here, and it's an improvement over the 35-minute mark, which was what I had last time. But this is long enough. I do have more I want to cover, so I'm going to make part 2. And in part 2, let's see here, what we're going to look at is I'm going to create some models that show an observer, a platform, and what happens to the light, the rays of light as they pass through an atmosphere, and how it gets distorted in different ways depending on different atmospheric conditions. We're also going to look at changing the height of the observer, and I'm going to be using some of BMLSB69's photos from his videos of the platform habitat as well. So that'll be part 2. Anyway, I hope you enjoyed part 1. I hope it was useful in some way. Key points I want to make here were that we're not seeing 15 feet of structure from the boat deck down to the water line, because I think we did not take into account, Bob, the science guy, and other people didn't factor in the reality that that 15-foot dimension was actually a sort of a maximum on the permit documents and not the norm. So we need to just, when we're looking at that bottom portion, which is critical because that's where there's so much happening. Certain people are saying it's compression and it's disappearing due to compression. Other people are saying it's being concealed by the water line, the curve of the earth. We need to keep in mind that it probably isn't 15 feet. I mean, it sounds like I'm nitpicking, but given that it's such an important part of the image, I wanted to stress that point. Also, I think it was interesting to see that although overall the structure seemed to get stretched vertically compared to its width, within it, it still had zones that stretched more and zones that actually compressed. So both things are happening. Random String was actually partly correct in his comment, his or her comment, which is that you can have both looming and compression at the same time, and we're seeing it in that image. We're seeing compression at the top of the structure, we're seeing compression at the bottom of the structure, and we're seeing the opposite. I've been calling it extension in the middle of the structure. And overall, the entire structure is extending or looming. Well, the overall structure is extending. The proportions are getting taller and narrower. As far as looming, that's actually not something we can tell from this photo. It would be, strictly speaking, something we could measure with surveying equipment. Is there less drop from eye level to the structure on the heavily refracted day? That would be looming. So I'm just trying to be really clear about what each of these things mean. Looming, the number of degrees of drop from eye level to the structure. That changes from one day to the next due to atmospheric refraction. When there's heavy refraction, we see looming, which means less drop. When there's standard refraction, we don't get looming. That means more drop. Now, we don't have those measurements for the images we're looking at here, so we really probably shouldn't be talking about looming, but we can talk about compression and what I'm calling extension. So those are the key points. Anyway, I'm going to risk rambling again, so I will say thank you very much for watching. Please hit the like button. Please subscribe. Please leave comments. That's the best thing you can do. I love to see people's comments. And have a great day. Bye-bye.